this video, we will go over the things that you should have learned so far from the simulation activity you've been working with, and talk about how to calculate the molar solubility when you know the value of the KSP. So far we've learned that solubility equilibrium describes the dissolution of relatively insoluble salts. So we've been looking at one example in the simulation, which is mercury 2 bromide, and when it dissolves in water, the solid breaks down into one mercury ion, that should be aqueous, and two bromide ions, each with a -1 charge. So each mercury bromide that goes into water, you get 3 particles out of it. So the KSP expression for this is the concentration of the mercury ion times the concentration of the bromide ion squared. And we've seen several different situations. If this Q, the current conditions, are equal to the KSP, so the amount of mercury and bromide ions present is equal to the KSP, then the system's at equilibrium. The solution is called saturated. That means that no more solute can be dissolved, and if there's more added beyond what the water can hold, then a precipitate, a solid, will form at the bottom of the container. You can see this situation in the second picture over here because no more solute can be dissolved, and so you can see a solid precipitate formed at the bottom of the container. We know from earlier in the year that if you're going to have a system that's at equilibrium, everything in the equilibrium expression has to be present so that you can have both the forward and reverse reactions. In this case, the forward and reverse things are mercury bromide dissolving into its ions and some ions reconnecting to the solid and precipitating. So we've got 2 processes, both happening at equal rates. The next situation is Q being greater than K. In most cases, if you try to put in more salt than the water can actually dissolve, then you will get something like that second picture where a solid, a precipitate forms until you get to conditions where what's dissolved in water equals the KSP. A few very select solutions can be supersaturated, which means under very unstable temporary conditions, you can get more to dissolve than should be physically possible. But if a supersaturated system is disturbed at all, the precipitate will quickly form and will come back to the saturated conditions. We'll look at an example of that hopefully in class. The other possibility is that the amount of salt that's been added to the water is such that Q is less than K, and we call this type of solution unsaturated. There's no precipitate present, and the system is not at equilibrium because you do not, if everything is dissolved, you do not have 2 processes occurring at equal rates. If everything's dissolved, you do not have solid becoming dissolved and dissolved returning to solid, so it can't be at equilibrium. More can dissolve. That is like the first picture up here where the system is unsaturated, it can dissolve more solute. So some definitions to move us forward to the next thing. Molar solubility is defined as the moles of solute that are dissolved, they're actually in the water as ions, divided by liters of solution. And solubility can also be, you can also define solubility as the grams of solute in every 1 liter of solution. We're going to look more at the molar solubility, and it's given the symbol lowercase s, and we're going to think about it like any other X in an ice table. You'll see what I mean in a minute. Some other things to review. What makes KSP change? Just like any K value that we've been talking about for the last 3 months, the equilibrium constant only changes when the temperature changes. However, the solubility of a salt, S, can also be changed when a common ion is present. We're going to look at that more, not so much today, but in an activity in coming days. And so the last question that we're going to answer on today's activity is, why can one not compare solubility by simply comparing KSP values? So I'm not going to answer that. I'm going to let you answer that, but we're through an activity that you're about to do. In this example problem, we're going to look at how to calculate the molar solubility of an insoluble salt using the KSP value. So when we know the solubility product value. So we're going to use an ice table because we're talking about equilibrium. And we don't know how much solid that we're going to start with. Frankly, as long as we have enough solid that it's more than can dissolve, that's fine. So we'll just say we have plenty of solid. But we're going to say that we start with nothing dissolved in the water. No mercury ions, no bromide ions. So we're going to use S here because we're talking not just about any old X, but this change actually is a name. It's called the molar solubility. So for every 1 mole of mercury bromide that dissolves, we gain 1 mole of mercury 2+ ion in the water, but we gain 2 moles of bromide ion. So something to keep in mind here, we've been dealing with acid-base equilibrium recently, and all the coefficients are 1. We got to remember now that we can have coefficients with these salts that aren't 1. And so for every 1 mole of mercury bromide that dissolves, we get 2 moles of bromide ion. So our change line, this needs to be 2 times the molar solubility. So after the mercury bromide dissolves as much as it can, and we're going to assume it dissolves at least enough to get to a saturated solution, then at equilibrium, our concentration of mercury is S and our concentration of bromide is 2S. Now our KSP expression, we have to write, and we're not going to include the solid because solids are never included in K expressions. So it's going to be the concentration of the mercury ion to the first power because the coefficient here is 1. But then it's going to be the concentration of the bromide ion squared because in a K expression, the coefficient becomes the exponent. So I'm going to then, I know the KSP value, I've given it, it's 6.2 times 10 to the negative 20th. The concentration of the mercury ion at equilibrium is S. The concentration of the bromide ion at equilibrium is actually 2S. So you have to be careful here that 2S is going to be squared. So this expression becomes S times 4S squared equals 6.2 times 10 to the negative 20th. And we're going to collect like terms here. So we end up with 4S cubed equals 6.2 times 10 to the negative 20th. And divide both sides by 4, so S cubed is equal to 1.55 times 10 to the negative 20th. And then I need to take the cubed root of both sides to just get the molar solubility, S. So by doing that calculation, I found that the molar solubility for this is 2.49 times 10 to the negative 7th molar. So that means 2.49 times 10 to the negative 7th moles of mercury bromide will dissolve in any 1 liter of solution. That is the molar solubility of mercury bromide.